So we're doing two-dimensional vector addition at this point, and what we're going to say is in two dimensions we have an x coordinate and a y coordinate, right? Something can be going left, right, or it can be going up, down. Maybe something floating, flying through the air like a projectile would exhibit two-dimensional motion if it's just going in an xy plane, as we say. So let's say, just for an example, that we have somebody here, and to use our last example, let's say that we have a guy who's walking. I'll put him in yellow because we started to say that last time. We have a guy that's walking in the eastward direction at 3 feet per second. And now remember, in the one-dimensional analysis, I says that there was a wind blowing from the west. Okay, so here you have east and west, and the wind was blowing from the west towards east at 1 foot per second. That's what we said in the last video, and we just simply added the two arrows because they were on the same line. Now, if the wind was blowing from the east, it would be working against them. So in order to get the addition of the two vectors, we simply subtract them because one's going in the positive x direction, the other vector would be traveling or going in the negative x direction, and we simply subtract them. But what happens now in this case if we have, for example, our wind blowing northward, and the wind is blowing in this direction at 1 foot per second? Now, in order to add these two vectors together, we have to do a little bit of geometric and algebraic manipulation. All right? We can no longer say that the result is going to be 4 feet per second. All right? We have to look at what's going on here and say, well, if the guy is walking along the x-axis to the right and the wind's blowing him northward, then the end result, and I will show the result of this, will be something that if I went over here to this arrowhead and I drew it like that, and I drew it down here and made a little box, then from the origin the result would be a vector going in this direction, and that is my result, or resultant vector, which is the addition of the yellow plus the blue. So how do we find that? Well, if we take a closer look at this by inspection, we see that we had a yellow magnitude of 3 going that way, and then we had upward. Now, here's the thing about vectors. It really doesn't matter whether we put it right here at the tail or here at the tip, and I'll show you why. So let's just keep everything on the tail. Let's put all the tails of the vectors together. And I think it's going to be easier in the long run to see it that way. This is a magnitude of 1. If we were to draw a box, and I just started to do that in red, so let's just draw a box here, then this diagonal of this box is going to be this 3 magnitude plus what's over here on this side. If this is 1 and this is a box or a rectangle, then this has to be 1 here. So we've got a right angle in here, and I'll show that in white. Here's my right angle. And this length of this vector here, which is the magnitude of the resultant, the length is going to be the square root of 3 squared plus 1 squared. The Pythagorean theorem, right? A squared plus b squared equals c squared, where c is the hypotenuse of a right triangle. Whenever you do vectors in 2 dimensions, you put all the tails together at the origin, and the vectorial sum or addition of each of the vectors is simply going to be using derived by using the Pythagorean theorem. All right, where you're going to take any two at a time and you're going to resolve them. So here we go. We had 3 in this direction, 1 in this one, so 3 squared plus 1 squared. So this resultant is going to be the square root of 10. That's the magnitude. What angle is this red vector, which is the resultant, going off at? If I put a little angle theta in here, do you know how to find theta? Well, it's a little bit of trigonometry, little geometry. The tangent of that angle theta, tangent is always defined with a right triangle. It's the opposite over the adjacent side. Tangent of theta is going to be the opposite over the adjacent side. The opposite side of theta is the blue side right here, which was the 1. The adjacent is going to be 3. So angle theta then will be the inverse tangent of 1/3. So now that we have the theta, we have the magnitude, which is the length of the vector that resulted from these two, the blue and the yellow. We have the magnitude. And we have the angle, and therefore we represent this as the resultant of the two vectors. In the next video, I'm going to show you how to decompose a vector at an angle into its two constituent perpendicular vectors. See, this vector here and this vector here are mutually orthogonal, or perpendicular. It's another name for orthogonal. When you have two perpendicular vectors, you simply use the Pythagorean theorem to find the resultant vector, and you use inverse tangent to find the angle. All right? Next video, we're going to show what happens when we have something like this and we have a vector that is off the xy, either the xy axis, and we want to show that we can take this vector and we can decompose it into two constituent xy components. We'll do that in the next video.